All right, we're in STL's office again, talking about STL. Introduce yourself for those
Convenient
who may not
how
know.
that works.
Yeah, it is really interesting
Yeah.
how that works, to be honest.
My name is Stephen T. Lauerwade, and my initials happen to be the same as Standard Template Library, which is a source of endless amusement.
But I mean, you work on the STL.
Yeah.
So, is there a connection between your name and your sort of native interest in C++?
I was actually using my initials even before I learned C++. It was just so convenient. And plus, they're just easier to spell than my last name, which is A's and V's everywhere. So I actually got them to change my email alias when I joined the company.
Outstanding.
Yeah, at first they gave me like S. Lauerwade. I was like, no one's going to type that, least of all me. You know, give me STL. And so they gave me STL. It's pretty cool.
So listen, we've been here, spent a few sessions in your office in the past. Beta 2's announced. Congratulations, you guys done a lot of interesting things.
I was so happy when I hit 0 bugs for Beta 2. I was like, yes.
Perfect. Null pointer. What's going on here?
So one of the interesting things that we're doing in Beta 2 is we added a new C++ OX core language feature. In the VC10 or VS 2010 CDP and Beta 1, we had 5. First we had 4, and then we had 5 in Beta 1. Core language features, lambdas, auto, static assert, R-value references, and decal type. And customers were always asking, and this is something they can really only do with the STL because it's controlled by this international standard. They know what features are coming. Like with Windows, I mean, we just invent Windows. So whatever's in Windows 8, well, that's what we decide. So people can speculate endlessly on
Windows 8 is just a code name.
Just a code name.
So
yes.
I'm not removing that.
Who knows what's going to happen like they did with Windows 7, which is also a code name that became the product.
Okay.
But whatever. Whereas with the STL, because it's controlled by, and the language itself, it's controlled by international standards. So if the standards committee releases a bunch of features in the working paper, then we're probably going to implement most or all of them at some point in the future. So customers have the ability to say, hey, when are you going to implement X, Y, and Z? And these are specific features that have already been put into final form or near final form by the committee. And we don't like promising new things, but it turns out it's actually easier to say this will definitely not be in so-and-so product. So people were asking, hey, are delegating constructors and so-and-so features from C++ OX going to be in Visual Studio 2010? Yeah. And after we released Beta 1, I was able to say the list of core language features in VS 2010 is only 5, and here's the exhaustive list. And so anything not on this list, we're definitely not going to be implementing in 10 because we don't have infinite time to release this thing. So, and with the libraries, it's sort of different. The thing about implementing anything in the compiler is that the compiler is insanely complicated. And changing one tiny little thing somewhere in the compiler affects tons of other things. You can think of most of the world's C++ ends up being compiled by Visual Studio. So if we break something there, it's a really big deal.
True?
Well, Visual Studio is the dominant C++ compiler on the Windows platform. Windows is somewhat big. C++ is a somewhat popular language, so most of the world's code is probably a majority.
The only reason I said that is because I'm wondering if applications like Adobe and the other sort of giant Windows applications, if they're not actually using our compiler.
Possible. There are
Studio.
other compilers like Intel's that are popular and target the Windows platform. Many people working on high performance, we need processor intrinsics, will use that compiler.
Sure.
But a lot of people just for the IDE, which is one of the most popular things we have, use Visual Studio at least for some portion of their product.
Totally, absolutely.
Yeah. So making
tool.
changes to the compiler is something that we have to do really carefully. We get world experts to work on the thing. Jonathan Caves, who implemented all of our C++ OX features, is on the standards committee. He's a wizard. He knows the language inside and out. So we have to sort of finalize the features that we're going to put into the compiler really early, like before we even start our first milestone of development, because it's really expensive for us to make changes later. Whereas with the libraries, the libraries are still being consumed by most of the people who use C++ with Visual Studio, but they're not nearly so interconnected. If we change something in regex, it doesn't have any direct effect on what we do in vector. So we can be adding features at a later point, we can be fixing bugs at a later point, which is why in VS 2010 we have added relatively more features from C++ OX than we have from the compiler, where in Beta 1 we only had the 5 features. But things always change during development, and relatively late, after we released Beta 1, we realized that we really needed to implement a 6th feature from C++ OX in the core language.
Great.
We had initially looked at all the features in C++ OX and said, okay, let's figure out, let's ask Jonathan, how long each of these is going to take to develop. Let's also consider how long they're going to take to test. Fortunately, we don't need to plan how long it's going to take to spec them out, mostly, because the committee's already done that work for us. And then we also had for each of these features to figure out how much users wanted them and would benefit from them. So something like lambdas was definitely high on the list, because pretty easy to implement. They're a completely new feature that it's not like a change to an existing feature. Users really want them because they love defining small function objects. And it would really benefit their code because it just helps them use things like the STL so much more easily. So Lambda, and also our concurrency team really wanted lambdas, because if you can package tasks in a lambda and then send them off for concurrent execution, they were really interested in that. It makes our concurrency features so much easier to use. So lambdas got on the list. Things like R-value references, somewhat easy to implement, kind of risky because they totally change the way that references work in the core language. But the libraries team, me, and Dinkware really wanted it because it allows us to unlock a ton of performance in the libraries. So our value references got in there. Not all the features that the libraries team wanted got onto the list. Like variadic templates is the remaining feature in OX that I'm totally drooling over. It allows you to have an arbitrary number of template arguments, which is really important when you write things like tuple. Pair is a little struct that contains 2 types. Tuple is a struct that can contain n types. The problem is you can't actually write such a thing in C++ 98. There's a way to fake it, which we've done in Visual Studio 2008, SP1, but it's really annoying for us to fake because we have to use the preprocessor. And the resulting mix of macros and templates is pretty horrible to look at, much less maintain. But we can get away with it. So because we have this workaround with the preprocessor and the fact that variadic templates would be quite difficult to implement in our current front end, and the fact that only the library devs would benefit, and users indirectly, but most users wouldn't be directly consuming variadic templates.
If I may interject.
Yeah.
The creator of C++ himself has said many, many times that C++ is a libraries language.
It is,
and
yes.
such that the library people should have priority.
They really should. And as a libraries developer, I'm somewhat biased to agree with that argument, but really C++ is a language for creating great libraries.
Yes.
And so variadic templates are very important for that. But just because the cost of implementing them.
Understood.
And when we were triaging the features, like, we really can't put this in 10. At some later point, we'll definitely have to get it. I've said I'll go on a hunger strike if I don't get it in the next release. We may or may not get it, but I'll go on a hunger strike if we don't. And so that's how and something like static assert, it's not the world's most important feature, but it took literally an afternoon for Jonathan to implement. So that got in. Nice. And so that's how we got our list of 5 features in Beta 1. But after we implemented all of that, and then we took advantage of them in the libraries, we realized that another feature, null putter, the new null pointer in C++ OX, we really had to implement it in 2010. And the reason why is that it's because we implemented R-value references. And R-value references enable perfect forwarding. And it turns out that when you've got perfect forwarding functions all over the place in the library, like make shared and pair and vector and all these other things, when you start passing null pointers to these perfect forwarding functions, it doesn't really work. It doesn't like crash, but it fails to compile with a relatively inscrutable error message as far as error messages go. And it's not a problem in the way R-value references work. They're doing what they're supposed to. It's a problem with the sort of, mashed together null that C++ inherited from C. And C++ OX has this feature called null putter that adds type safety to the null pointer. And when we first looked at it, and this was as we were beginning VC10's development, we looked at it and said, type safety for the null pointer would be nice, but we're using the current all caps null just fine. It doesn't look like any other feature relies on this, so we're going to categorize it as low priority, nice to have, but if we don't have time for it, it's not going to get in, and it didn't make the cut of the 5 features that we were going to implement in beta 1. But then we realized that, oh wait, null pointer really does interact with R-value references. And had we known that when we started 2010's development, we certainly would have done null pointer at that point. So essentially we made a mistake in saying, oh no, it's not related to any features. And then in beta 2, we've gone back and corrected that mistake after we realized, both the compiler and libraries, that wait, this really does interact very strongly with R-value references. It's not just some sort of nice-to-have feature that closes a hole in the type system. It actually, at a very fundamental level, is important to have when you're working with perfect forwarding. So we have a 6th core language feature. This time we're swearing it's the last feature. We really can't implement anything more between now and RTM.
Sure.
And in fact, when we implemented this thing, we categorized it as a minor bug fix. Not a bug fix, certainly not a DCR, design change request. It's probably a little exaggeration. But yeah, it's pretty important when working with perfect forwarding.
Excellent. So, without further ado, we should talk.
You want me to show you what it looks like?
That would be nice.
Okay.
And also, maybe give us a little bit of a refresher on perfect forwarding, because
Yeah.
you talked about that, everyone, extensively in the last video we did with you, and Damian Watkins joined us for that as well.
Yeah.
But go ahead and give us a little refresher, just a brief one, and then dig into null pointer. Since you're very good at the whiteboard, we like to get you up there, man.
So imagine that you're using shared pointer. Everyone likes using shared pointer, or should. And you are going to be dynamically allocating foo objects. So we have a shared pointer to foo, and let's call it SP. And we're going to construct a new foo. So new foo, this is all in one line. I just write big. New foo, and then we're going to give it some constructor arguments. So this is awesome. We end up with a shared pointer that owns a foo. And this contains, whatever awesome data you put into it with these constructor arguments. Then you can go use it. So if foo has a member function bar, you can say sp arrow bar, give it some more arguments, it'll go do its thing. And then when the shared pointer goes out of scope, it's going to delete the foo, goodbye foo, for you. So you don't need to say delete p in your source. And this is what we shipped in 2008 SP1, or VC9 SP1 as I like to call it, because it's short. And this is what TR1 provided. TR1 is a set of extensions to the existing C++ 98 standard library. Okay. That's library-only extensions, sort of an intermediate step between C++ 98 and the new C++ OX standard. In C++ OX itself, we can take advantage of new core language features, which is something we couldn't do in 2008 or TR1. And so shared pointer is now in C++ OX. Originally it was stood TR1 shared pointer, saying, here's some TR1 extensions. They're not officially part of the standard library, but they live in a sub-namespace. They're extensions that are blessed by the committee, but they're not quite an international standard. So this was in TR1 or VC9, SP1. In VC10, or VS 2010, which is C++ OX, This has been promoted, and it's now an official member of the standard library.
Dun, dun, dun.
Yes. Blessed by the committee twice over.
Nice.
And it's just standard or stood shared pointer. So it still works just like it did in TR1. And even before that, Boost, which is the open source library, it was initially implemented and designed by Peter Dimov and the other Boost developers. So this syntax still works. So code that compiled with TR1 or with Boost will still compile in C++ OX. It just lives in a different namespace. So if you've got your using declaration or directive there, you don't even need to change your code. But if you want, you can now use new things provided by C++ OX. And one of them is a convenience function that makes constructing shared pointers easier and more efficient. So now in C++ OX, you can say this. Auto, and I'm just going to use another language feature that we have in VC10, sp equals make shared foo args. And then you can go use sp and say sp bar just like you did before. So what this function make shared does is it does two things, 2 in 1. It both constructs a foo and a shared pointer that owns it. And then we get this as sp. And then we're using, so the return type of this guy is shared pointer of foo. This auto keyword is a C++ OX feature that says, make the type of this variable the same as whatever initializes it. So because make shared returns a shared pointer foo, the type of this guy is shared pointer foo as if you had written that by hand. It simply saves a ton of typing, and if for some reason you initialize it with something else, say you start constructing a shared pointer bar here, then the the type of this guy will automatically change.
Sure.
So that's a great win for convenience.
Certainly.
But it's only syntax. It's not changing the runtime behavior of a code or anything. So what make shared is doing is constructing the foo. So you've got the foo, and it's constructing the shared pointer that owns it. It's also doing something a little more efficient, and this is something we couldn't do in VC9, and that is saving memory. So when you construct a shared pointer by hand, say if I have shared pointer, and I'm going to call this one just, say, x, new foo, whatever. What this looks like is you've got your shared pointer x here, and it owns this foo. X, the shared pointer, is the size of 2 raw pointers, because that's what it stores. And this foo is however big a foo is. We've got some allocator overhead here, maybe 8 or 16 bytes, depending on your platform. And it also needs to store a reference count. Shared pointer is non-intrusive, so the reference count that it stores is not part of the object itself. This is great for usability because it means you can hold anything with a shared pointer without having to derive from some ref count or put a reference count inside it, like you do, say, with COM, which has intrusive reference counting. With shared pointer, the shared pointer will construct a reference count control block for you. So this contains a bunch of things. It's got a pointer to the object itself. It's got a strong ref count. It's got a weak ref count because you can have weak pointers that break cycles and can observe this object. And it also has a vtable pointer in here. That would be up here because we've got some virtual functions going on, and then some more allocator overhead. So great for usability, but we're paying a second dynamic memory allocation. This is not so awesome in terms of performance. It's not the end of the world, but in something that is creating a billion shared pointers, or a million, you would definitely notice this. When you call make shared, though, we can do something pretty clever because we're both constructing the object and a shared pointer to it. So when you call make shared, this optimization, which is suggested but not required by the standard, essentially every library developer who knows what they're doing will implement this optimization, as we have done. What will happen is you'll get a shared pointer, still the size of 2 raw pointers, that hasn't changed, and it's going to own a foo, just like before, which is however big a foo is. But it can store the foo and its reference count in the same memory block. So you get a memory block here that has a strong ref count, and initially it's going to be 1, a weak ref count, and this will happen to be 1. And it's going to have a vtable pointer, but that's it. And we pay only 1 dynamic memory allocation instead of 2.
Nice.
And we actually get to save an extra raw pointer because we know where the foo lives. So depending on how small your foo object is, the overhead that we save could be as big as 2x. So we could be consuming half the space. And it's faster too because we only have to call our memory allocator once. And then when the object is destroyed, we only have to call the deallocator once.
Excellent.
So make shared is both more convenient because you only have to say the type name once, and it's more efficient. It's a win all around. It also avoids a particular pitfall of constructing unnamed shared pointers that I won't get into. But if you look carefully at what make shared is doing, it's having to do something interesting. So make shared is a library function, and it's going to work with user code. In this case, whoever implemented foo. And what it's going to do is it's going to want to be able to work with arbitrary foo. And this is a big thing of library developers. When we say arbitrary, that means we get to exercise our smarts. And working with arbitrary foo means that we need to take an arbitrary number of arbitrary types for these constructor arguments, because we don't know what the foo can be constructed with. Maybe it's constructed with an int, a double, and a pointer, or maybe 10 pointers, or maybe an enum, a reference to some other struct. I mean, you're the designer of foo. I'm sitting here designing make shared, and you're the user. You've designed your foo. I have no idea what it's going to take, but I need to be able to forward these arguments to foo's constructor. Because inside make shared, you can imagine that I'm going to write, and here I've got, I'll show you a little more of this declaration. I'm writing make shared, so I'm going to say template, type name t, and I'm going to return a shared pointer t. I'm inside namespace standard, so I don't need to say standard here. And then I'm going to call myself make shared. And then I've got to write arguments, blah, we'll get to that. And then inside here, I need to say something like shared pointer t, new t args, return, I need to give this guy a name, ret, and then return ret. Now I'm not really doing this because this doesn't do that particular optimization. Instead, I need to call some other machinery that's going to allocate a reference block, reference count control block and the object all in one. So I'm skipping over that. But the important thing is that I need to say this. At some point, I do need to construct a t object with these arbitrary arguments. So what this requires is perfect forwarding to be able to accept arbitrary arguments. It also requires variadic templates because I could be given 0, 1, 2, a billion arguments. There we fake it because we don't have variadic templates and even VC10 by overloading make shared 11 times for 0 to 10 arguments. We stamp it out with preprocessor macros. So let's just assume that I'm going to do this for 2 arguments, because if I can do it for 2 arguments, I can do it for as many as I want. When we write a perfect forwarding function, what we have to do is we have to template this on type name. I'm just going to scribble here, A1, type name A2, and we take A1 ref A1, A2 ref lowercase A2. And then here, where we've got that return ret, constructing this t, we need to say new t forward. This is a function in the C++ OX standard library. A1 forward A2. So this type A1 ref A1, this is an R value reference. And then this construct here where I'm templated on A1, I take A1 ref A1, and I say forward A1. This is known as perfect forwarding. The language rules that this uses are somewhat arcane. I have a epic length 50 kilobyte blog post that explains in detail how all of this works. But at a high level, you can think of this declaration as saying, I take anything. And then when you say forward A1, it means I give whatever that thing is to T's constructor. Meaning it could be an int, it could be a double, it could be a reference to some class, it could be a pointer, anything. And this works. Anything that you could possibly give to T's constructor, you can give to make shared, and we'll pass it unchanged. And this also, and because library developers are really big on genericity, it works no matter how you define T's constructor. Maybe T's constructor is itself a template. Maybe T's constructor is overloaded, and you've overloaded it to take a pointer and a pointer versus an integer and a double. Make shared will allow your call to make sure to compile if directly constructing that T would compile to. And if it doesn't compile, then make sure it won't compile either. So it's perfect in the sense that it exactly matches. It's not transforming the arguments in any way. It's not prohibiting you from giving it pointers or doubles or R values, that sort of thing. So perfect forwarding is pretty awesome. That was something we had in beta 1. The problem is that we've got this make shared signature, so now I'm going to erase this because we know what it looks like. And now I'm going to have some class. Say I'm going to call this class meow. I like cats. And I've got, some data members or something, but I'm going to have a constructor, a meow. And meow is going to be constructible from a couple things. An int, x, and let's say a double pointer, p. And then it's going to go do stuff with them. I don't know what it's going to store. Maybe it'll store x and p, and then modify x and remotely observe p, whatever. Mostly I'm interested in the fact that this constructor takes a pointer. Then, suppose I go, using VC10's features, I say auto sp is make shared. And suppose here I've got an int n is 1729 and double pi is 3.14, terribly inaccurate. And I say make shared meow, and I'm going to give it n and the address of pi. This will compile. And then I can go, call things on it, feed me. That's what cats like to say. This totally works. Now imagine that I define meow so that it can also accept null pointers. Maybe if I pass null as this argument here to double star p, it just means I don't have a double. So go use 0 or print null or whatever. You're just not getting a double today. So if that's the case, I could say meow m, 5, and then null. Like this. This will totally compile, and then I can say, m dot feed me. So I can totally pass null pointers as my double star. Now imagine that I try to do the same thing with make shared. I say, as before, auto, and this time I don't have pi. I say auto sp is make shared meow n, and then here I try to say null. The world explodes. Oh, you're going to get a terrible compiler error right here. And it's not going to be pretty. It's going to say something deep in the guts of make shared's instantiation. Something like error C1234, I don't know what the number is, cannot convert int to double star. No conversion is possible. Do you mean to use a reinterpret cast here? Blah, 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 blah. And it's going to be complaining not in your code, but in the header where make shared is defined, which would be somewhere in either memory or more likely in our subheader xx shared, which is where we actually implement this due to that preprocessor stuff. If you look at the line that it's complaining about, it's going to have all this preprocessor magic in it that we're simulating variadic templates with. It's not going to be pretty. It's going to be arcane library internals that you've never seen before, you don't want to see. And it's not going to be obvious what went wrong, because you totally can construct a meow with null. But why can't you say make shared? And the reason why is sort of depressing because it comes from C, and everything that comes from C is sort of old and depressing. And the reason why is that null is not really a first-class citizen of the type system. Null is a macro, and if you look where null is defined, it looks like this. Define null to be 0. In C++, null is going to look like this or almost like this. The standard permits a couple other things. You can actually get it to be 0 of type long or unsigned long or that sort of thing. But null is basically going to be an integer whose value is 0. And then the language has special rules that say if you say something like double star p is 0, 0 is of type int. This is of type double star. If I tried to say like p is 5, this will totally not compile. And of course it shouldn't, because let me put here double. Because you can't convert an integer to a pointer. That's just nonsense, implicitly. However, if you say double star p equals 0, well, 0 is so popular as the null pointer that the language has a special rule. And it says, if you have an integer constant, an integer literal, of value 0, then yeah, you can convert that guy to a pointer. Its value is going to be the null pointer. And so then, to give it a nicer name, it's been macroized to all caps null. And this seemed to work, pretty fine for the last 20 or so years. The problem is that as we accumulate things like perfect forwarding functions like make shared and pair and so forth, especially in C++ OX, the problem is that 0 just doesn't really cut it anymore. So imagine what happens when we call make shared with null. So recall that make shared signature look like type name, template type name. In this case, it's going to be A2. Make shared taking stuff A2 ref A2. And then it says forward A2 A2. So when you call make shared, it has to first it's going to find make shared declared in our header. Then it's going to perform template argument deduction. Because you called a template, make shared, you gave it some template arguments, the t, which you want to construct, but you didn't give it other template arguments. In this case, the types of the arguments for the constructor. It has to go deduce them for you. This deduction is what powers perfect forwarding. And so if you call it with null, null has been macroized. So even though you said end null, the preprocessor is going to put a 0 here. That's what the preprocessor does. It doesn't know anything about the language. It just loves replacing text. So template argument deduction is going to do whatever it does for n. It's going to deduce that to be of type int. Then it's going to look at this 0. It's going to say, what type is 0? 0 is of type int. So A2 is going to be deduced to be int. And so that's going to be substituted in. We're going to take an int ref, and then we're going to forward it. So we can totally pass 0 to an int ref. Perfect forwarding will accept arbitrary things. The problem happens when we try to pass this int here. This is forward int, and to t's constructor. This is going to be meow. So I'm going to call meow's constructor with the result of this. You can ignore here what forward int is going to do. It's just going to return a reference to this int. The problem is that now we are trying to pass a reference to an int to meow's constructor, which wants a pointer. We've forgotten a crucial bit of information, and that's the fact that we're being passed the 0 literal. We can convert the 0 literal to a pointer. We cannot convert some arbitrary int to a pointer. And nothing in the system of templates and template argument deduction lets us remember the fact that this guy is so special, his value matters, not just his type. So it'll fail to compile here, saying, whoa, I can't convert an int to a pointer. Or you can imagine even worse things. If meow's constructor has been overloaded to take something like an int and an int, then this one will be selected. So it'll compile and then do something crazy. Or potentially even worse. If this guy is itself a template, the error could happen when you're instantiating meow. I mean, total badness. So this is why the null macro and 0 as the null pointer don't really work so well in C++ OX. So now, what I like to say is, if you like your null pointer, you can keep it. So if you like writing all caps null in C++ 98, then you can keep writing that. It'll continue to work. The definition of null in C++ OX is not changing. So in our implementation, it's still going to be 0. We're still going to define it to be 0. the committee considered changing this and then realized that it would probably break the world, and in fact it would, because people not only use null in crazy places, they misuse it as a plain old zero. I mean, I've found in Visual Studio's own code base people saying things like index equals null. They want x to be 0, but they said null. This is just bad from a conceptual point of view. Or people saying things like char c equals null. Here they want the null character, which is not the null pointer. What they should have said is, single quote, \0, single quote. But as long as null is defined to be the integer 0, you can get away with both of these.
Mm-hmm.
Breaking the world is not so fun, so this macro will still be defined to be 0. However, if you start trying to use the macro null with perfect forwarding functions like make shared or pair, things like that, it'll start to break mysteriously. So C++OX comes to you and says, I'm going to give you a new, fancier null pointer that you can use. And this, after a lot of deliberation, was named nullputter. And I deliberately pronounce it nullputter to make it sound different than null pointer. This is all one word, no underscores, no capitals, no nothing. And what this is it's a constant of nullputter type. In fact, this guy's type is nullputter t. This lives in the header standard def.h, if you really want it. And what this is this constant is convertible to any pointer type. So if I have a double star p, I can say double star p equals nullputter. And it's convertible to double star, as if I had said 0. However, it's not convertible to other things. So if I say something like int x is nullputter, this will not compile. No, no, no. Because this null pointer type is not convertible to an integer. Or if I try to say char c is nullputter, will not compile because it's not a character. It's a null pointer. Mm-hmm. So that type safety is nice. And this is what we looked at the beginning of VC10's development and said, you know, this is nice. It closes this sort of defect in the type system. Now, the thing is, this defect didn't really rise to the level of permitting really incorrect code. It permitted things that were not really kosher, but you could get away with. So we looked at that and said, you know, it's not worth the time to implement it for 10 because we're doing so many other things in the compiler. Let's save our time for more important features like lambdas. So we didn't implement it in beta 1. Then we had things like make shared, and we noticed that we couldn't pass null the macro to it. So when you have nullputter, the story changes. The magic of nullputter is it's not really magical in and of itself. It just has the right type. It's no longer encoding the fact that it's a null pointer in its value. The mere type nullputter t is enough to say, hey, I'm a null pointer. Go, convert me to a real double star or whatever. So if I call make shared, no longer exploding, with nullputter, what happens is that when I'm calling make shared and I perform template argument deduction, make shared is blah blah blah, taking a2 ref a2, and then it passes to t blah blah, blah forward a2 like this. Here we're passing it the null pointer literal nullputter. So this type here gets deduced as nullputter t, because that's the type of the nullputter. And then here we just substitute it in. And so when we call this function, nullputter is totally convertible to nullputter t ref. It will directly bind, it's the right type. And then it can be forwarded as nullputter t. And crucially, we can convert this nullputter t to double star. Because any nullputter, and they're all the same, can be converted to any raw pointer. Excellent. We've remembered the fact that, hey, you're bringing us a null pointer. So nullputter makes perfect forwarding work for things like null pointers.
It's like a generic pointer.
Exactly. It's convertible to any raw pointer.
So how did you implement null pointer? Anyway.
So the interesting thing about nullputter is, well, I didn't implement it. Sorry. It was Jonathan Caves.
Sure, but I'm sure you understand.
Front-end wizard. I was the first consumer of it in the libraries. Yeah. In fact, what we did while implementing it is we took VC Tools, which is the part of Visual Studio's code base that consists of the compiler, the standard library, a couple other things like the name undecorator, the linker, but not the IDE. It's only sort of the compiler and toolset. And what I did is I went into our headers and I actually defined the null macro to be null putter. At the time, we were actually operating under the delusion that the committee required this. So I tried to get vctools to compile with the null macro set to null putter, and it exposed all sorts of problems like people assigning it to ints and characters. It also exposed bugs in the feature that Jonathan was able to fix, which was great.
Excellent.
And then later we realized, oh, we're not supposed to change the null macro, so I went and undid that part. But we had at least gotten some real-world experience compiling all of the tool chain with null putter everywhere people were saying the macro null. And when Jonathan implemented null putter, the interesting thing was it was already implemented in C++ CLI. When we did all of that managed stuff, we have this managed null putter, which is not so conveniently named null putter just like this. So most of the code was already in the compiler, which has to understand both native and managed under /CLR. Jonathan just had to add additional tweaks to make null putter the native null putter, not introduce any of that managed stuff. So if you're compiling without /CLR and you say null putter, you're not going to get any managed code in your process whatsoever. Still completely 100% native. It's just that we're using some of the same logic that was implemented for C++ CLI.
Yeah. Well, you guys focused for many years on that and did some great work.
Yeah, and so now null putter is available in native code because it was standardized by C++ OX. Now, the reason I said not so conveniently is because null putter kind of breaks a promise that we made, and that's you can always take your code, that's C++, and compile it /CLR, and it will just work as managed. The problem, and this is one that we sort of dug ourselves into, because we went and added null putter to C++ CLI, and then we went to the C++ standards committee, and we said, hey, null putter would be a great name for your feature. And it's already in C++ CLI, except the fact that it has different semantics in native and managed. So when we went to implement it, we were like, well, we need to separate the native and managed null putters. The problem is that they have the same name, so what do we do? So the answer is kind of annoying. Fortunately, it will only really affect people who compile code under /CLR constantly. And now our story is that /CLR is just for interop. You're not supposed to be compiling entire, megabytes, millions of lines of code under it. Only your interop layer. So in native, if you say null putter, this one is native.
Okay.
In managed, and this is like /CLR or /CLR pure, which I'm not sure anyone actually uses, but we support. If you say null putter, this is managed. So you see the problem here. This is the behavior that we supported in VC9, Visual Studio 2008. This is mandated by C++ CLI, which is an ECMA standard. This null putter is new to VC10, and it's mandated by the ISO standard, ISO C++. Good old 14882. They have the same name, but they have different semantics. Now this isn't a problem as long as you're strictly on the managed side. If you say null putter, you get the managed null putter. Or you're strictly on the native side, you say null putter, you get the native null putter. But if your code that's going to be compiled is either, or if you're managed and you actually want the native null putter, for example, you're writing new code, then you need a way to access this guy from managed.
Okay, so I mean, but so I think the confusion that arises out of this is definitely understandable. So
yeah,
regardless of the fact that they're actually named the same thing,
they're different things.
They're different things, but the concept of null pointer,
concept is the same.
So why are they different things? I mean, in some sense,
that's a pretty deep question. Jonathan will be able to answer it better than I can.
Fair enough. So
this null putter and managed brings along its own semantics. Like it's usable in generics. It's usable in places that native null putter isn't, and vice versa.
I understand.
For example, one bug which was filed against me is that you can't actually pass this managed null putter to a perfect forwarding function. It just doesn't work like that, whereas the native null putter does. So since I sort of live at the libraries level, I don't know exactly what's happening in the compiler, but they definitely have different semantics.
Okay, so
we weren't able to unify them.
Okay, good. So Niners and people watching, understand this.
Yeah.
So I mean, because I would imagine there are some people using C++ CLI.
Yeah, we told a lot of people to start using it, and they did. So if you want the native null putter when you're compiling /CLR, we have added as an extension, and this is actually not so evil on the evilness scale of our extensions, a new keyword, double underscore null putter.
Oh, the double underscore has returned, ladies and gentlemen.
Yeah, people hate double underscores because they're ugly, and we try to avoid them whenever possible. But the other thing is that we have free reign to have double underscore identifiers, and people at least find them a little prettier than the other alternative, which is capital.
Yes.
Underscore capital. We use this in the standard library all the time. So if you're just a plain old user, you should not be using underscore capital or double underscore identifiers in your own code. That's the compiler and library implementer's namespace. The whole reason why we choose these ugly names is so we don't stomp on user macros with our extensions or keywords. But if you need the native null putter managed, you can say double underscore null putter, and it's guaranteed native. And then also, and I only recently learned this is also available in native. So if you say double underscore null putter, it's always going to be the native null putter. We use this in our headers just because our headers can be compiled either native or managed, and otherwise we would have to if-def. Here, if we just say double underscore, we always get native. So Perfect. It's ugly. We wish we could have avoided it. We didn't. And I don't believe that they can actually be unified. Have a single name that's either the native or the managed in context. I believe if we could have, Jonathan would have implemented it that way. So because they can't, we have to give them these names. So a little bit of it doesn't quite work if you compile /CLR. On the other hand, it shouldn't cause people too much pain. So because they're going to be writing completely new code with null putter. But the great thing about null putter is that once you're aware of this annoying little problem, you can then just start saying null putter, assuming you're strictly on the native side. I'm going to erase this now. So suppose you're strictly in native land. You can start, instead of saying null, this is old. You don't want it. You can start saying null putter. This is new. This is happy. Null putter, you can say anywhere. You would have said the null macro, and it will compile as long as what you were going to say was legitimate. So doing things like initializing int x with null, that was a bad idea to begin with. Null putter will not allow that. But initializing any raw pointer with null putter, totally good. So it'll totally work. And null putter will work better with perfect forwarding functions. So excellent. Once you have VC10, you can just sort of turn your brain off. Anytime you want the null pointer, say null putter, and it'll just work. And you won't have to deal with horrible template error messages and make sure and that sort of thing. Beautiful. So that's sort of the story of how we implemented some features, discovered a mistake, and then went back and made it right by providing this feature that works at a very fundamental level with R-value references. Now, if I could go back in time to the beginning of VC10's development and just tell myself that, we would have saved so much misery. It would have been in beta 1 to begin with, and we wouldn't be talking about it now. It would have just always been there. Well, at least we caught it in time for shipping.
That's the organic process of developing software, especially generalized software.
Yeah, there's all these moving parts, and we didn't quite understand when we first looked at it how they interacted.
Absolutely.
Yeah.
So, who knows? You might find out other things. I do think,
that's the problem with trying to implement C++ OX piecemeal, is that all the features really do work together on some level, like variadic templates and R-value references. They really want to go together, because you can write really nice things together with them. And we have one but not the other. We have to live with that. We saw that one far in advance. Here, it took us a while to realize.
Sure. Well, you can't do everything right.
Yeah.
Right off the bat. But come on, that's a lot to implement. I'm sure 6 new language features is a lot in a language like C++.
Yeah, and then having to go rewrite most of the standard library in light of them to take advantage of R-value references. We had to give some standard library types constructors from null putter T, so forth. We even went back to things like ccom putter and some other ATL types that do things like wrap pointers, kind of like shared pointer does, and gave them null putter constructors, so you can give them null putter. We may have missed a couple places, but we try to get every place we could think of. And in fact, we closed some significant holes. So one of the problems I'm pretty sure with ccom putter, is that people love constructing these guys from the macro null. So they love being able to say ccom putter p to stuff p null. The problem is, if you look at this interface, it's constructible from a ton of raw pointers, like 2 or 3, maybe more different types. It's constructible from like X star and Y star and Z star, where these are like, you know, interface types and whatever. So if you have a type that's constructible from a single raw pointer, then you can pass it null without, and this is the null macro, without any further work, because null is convertible. However, if you're constructible from a bunch of different raw pointers, this will no longer work. It'll say, which one do you mean? Because null, which is just 0, is equally convertible to X star, Y star, and Z star. All those conversions are possible. They all have the same rank. So overload resolution, which is the part of C++ that tries to figure out which function you meant to call, in this case, which constructor, says, they're all equally good. I don't know which one you want, and it'll fail to compile. So, and you could work around this by saying, you know, static cast or just use a ccast to X star, saying this is the pointer that I want. But when we design when we designed ccomputter, we didn't want people to do that. So we gave it not only constructors from X star, Y star, and Z star, but also from int. And 0, because it's of type int, will bind to this constructor. It's an exact match. And then we asserted that that int should totally be equal to 0 and not like 5. And then we went and initialized it with null. In C++ OX, we can't really do anything about this particular atrocity, but we've given it a null putter t constructor. So if you construct it from null putter, it'll select this one.
Okay.
In a couple places, I can't quite remember, I'd have to look it up, whether it was ccomputter or not. The interesting thing was, it was actually constructible from a single X star, and we gave it an int constructor anyways. And then when I went to, you know, add null putter to all the types that needed it as constructors, this was when I was compiling these tools with null putter, I looked at this and I said, you know, we don't need this int constructor. If I simply remove it, then null the macro, which is the same as 0, and null putter will both select this, because they're both convertible to X star and there's no competing raw pointers. This closed an important, nasty loophole in these constructors, and in fact, as soon as I did that, something else throughout the Visual Studio build failed to compile, and it turned out what they were doing was, and this will make you groan, they had some function that returned computer. At this point, I think it was ccomputter that I was able to remove the int constructor from. So this was a ccomputter to something, some function, and at some point they were doing things like, you know, return sp, you know, lots of code, and later on they encountered some error, and they said return e out of memory. You know, because lots of h-result returning functions will say this. The problem is they said this in a function that was returning ccomputter. This actually compiled in Visual Studio, and it selected that constructor that took int, because hresult is convertible to int. It's like an unsigned long or something. Now that would have triggered an assert as soon as it happened in debug mode. In release, it would just silently compile. Whereas they really meant, in this case, this code used the convention of throwing exceptions. So as soon as I removed that int constructor, this failed to compile, and we were able to convert this into the right thing.
Good.
So it's not
Nice
always
job.
possible, because we had to retain those int constructors in other places to allow code that was using the all caps macro to continue to compile. But in every case we could, we removed these unnecessary int constructors.
Perfect.
And like in the new world, if we were designing something that was constructible from X star, Y star, and Z star, and we wanted to make it easily constructible from null, we would add a null putter t constructor. And so if you give it a real pointer, it'll select the appropriate constructor. If you give it null putter, it'll select this one. If you give it 0, it would be ambiguous, because 0 is actually convertible to all of these. But 0 is the old null, we don't like it, you know, so much, it has problems. Whereas null putter is the new nice null, and it would select this one.
So and of course, in terms of compilation, if you detected that somebody was doing that in this new world or a new library that you created, you could just tell them, hey, you would be able to give that information back during either a warning or just...
You mean that they're trying to convert null putter to something...
Yeah.
Yeah, you actually get a compiler error saying null putter T is not convertible to int or
Exactly.
char. In fact, it has a very restricted set of conversions. So in terms of types, you got your null putter T. So it is convertible to any pointer type, so like T star. This is totally cool. It also happens to be convertible to bool. I'll skip over that. That's so people can test it.
Okay.
I'm not convinced that that is a good idea, but at least it doesn't come up very often. And you can also convert the literal 0 to null putter T, but no other conversion. So you can't convert like arbitrary integers, like int n. This is no. Cannot convert. And null putter cannot be converted to like int or char or any of the other things that 0 can be converted to. This is no. It really locks down the conversions, so you can only convert it to raw pointers. The reason why you can convert 0 to null putter T is
Definition of null.
is because that's what null has been macroized to.
Yeah.
And although this is sort of not elegant in the type system, permitting it to be converted to null putter T doesn't open up any loopholes.
And
in
actually,
fact, makes things more
null,
usable.
one could have a philosophical debate over whether or not null is 0. And why is it defined that way? We don't have to get into that.
If we were defining C++ from scratch,
Yeah.
null would just be macroized to null putter.
pointer.
Or in fact, it
Yes.
wouldn't be a macro at all. Null would be null putter, and it would be less typing. The problem is that we didn't understand this, and this would be back when C was designed.
Okay.
This was not understood enough, and then when Strustrup did C++, these sorts of concerns weren't clearly understood enough. Null defined to be 0 was working out for everyone.
Okay.
Compilers were exceedingly primitive back then. Of course, I get to speak from 2009, where our compilers are advanced. They were doing the best that they could with the technology at the time.
Yeah.
But now we know better, and we have advanced libraries that do things like perfect forwarding that were literally unthinkable when C++ was first created before templates. And so now things like having a type-safe null are really important. So that's why we're getting null putter now. Would have been nice to have 20 years ago, but at least we have it now.
Type safe null, I
Yeah.
love it. Excellent. Well, we spent the whole time today on null pointer and a lot of history.
It's a core language feature, but I'm a libraries developer.
Well,
but
that's-
it
but
sort of
has
straddles the
profound
fence.
impact. Come
Yeah,
on.
it's
Got
usable
profound impact
with
on you.
make shared. Yeah,
Very cool.
and then there's other things we're doing in beta 2, like R-value references v2. We're the first compiler, as far as I can tell, to be released in production with this change to R-value reference semantics, and we had to go do a bunch of work in the libraries to make that happen. Lots of other features, but this is the major new feature that you're going to see in beta 2.
Excellent. And
That people should
maybe
use.
next time we can talk about iterator debugging.
Yep, iterator debug level. We changed the defaults there, added a new linker pragma that will automatically be used by the library headers. So the good news there is that unlike null putter, which users have to learn about and start using, with the work that we've done in iterator debug level, you either get the new default that improves your performance, or you get the new pragma that detects mismatch problems at link time, and that's all done for you. So if you screw it up, you'll get a nice linker error, and then you have to go fix that yourself. But you don't have to take any action yourself to take advantage of the new pragma or the new default.
Perfect.
So, yeah.
So right on. Beta 2, play with it.
Yeah, and we really need users to report bugs in beta 2 in like a timely manner. Sometimes, we release like a beta, and it's not a complaint because our customers are as busy, if not more busy than us. But we'll release a beta, and then like 3 months later, we'll get bugs filed against it. That's not so useful because by that time, we're essentially locked down the product and we're about to ship it, and that's much more of an issue for beta 2 than beta 1. With beta 1, if you wait like 3 months to report a bug, we won't be able to fix it in beta 2, but we'll be able to fix it in like RTM. I'm currently fixing some bugs like that. But if you wait several months to report a bug you found in beta 2, you're essentially guaranteeing that you're not going to get a fix in RTM, which is probably not what you wanted. If you're reporting a bug, you probably want to fix it as soon as possible. Yeah. So it helps the customers, it helps us. If people will like download betas as soon as they come out and report bugs as soon as possible, like within weeks, if possible. The longer that they wait, the more likely it is that we're going to just due to the constraints of time, have to triage it and say, this is going to have to wait for the next service pack, or worst of all, wait for the next release. Because our releases, are on the order of years, and if you have to suffer with the bug for, a year or more, that's not going to make you happy. It's not going to make us happy that we couldn't fix it in time. We love to fix bugs if they're reported to us in time.
Understood. Well,
So,
I mean, and one could say that, we're sort of, I would argue, at the tail end of a world where that's the pattern.
Yeah.
In a world where we have modularization, where we have real composability, real compositionality,
Yeah.
you could fix these bugs.
On a
and it would
fast
just
release
fix.
cycle, yeah. The other problem is that currently, and we're trying to improve this process, releasing hot fixes is a lot more expensive than people expect it is. We released a couple hot fixes for VC9, Visual Studio 2008, in the standard library, and this was literally hacking, I always say hacking, fixing like 5 headers. These are just header files, not even any sort of separately compiled files that go into the DLL or things like that. And just releasing that involved a multi-megabyte hotfix package that we screwed up and had to re-release because it wasn't sequencing properly with other hotfixes. It required multiple weeks of testing. It required lots of people, and the process should be faster, but I believe there's a limit to how fast it can get, because if we're going to release something like a hotfix, we need to be really sure it's not going to break things.
Sure.
So we need to devote a lot of scrutiny to it, and that's individualized scrutiny. Whereas if a bug is reported to us during development, we can just go fix it, and then it's going to get tested as part of the whole product, and it has a lot longer bake time. So it's always going to be easier for us to fix things during the release, regardless of how fast we release. So that's why I say, hey users, please report bugs through Connect or the forums or whatever process they like. Connect is the most convenient for us.
Great.
We can actually get to fixing them
Perfect.
as soon as possible.
Excellent. All right. Well, hey, thank you for your time again.
Yeah, nice
Always
talking to you.
great to chat with you, man. Great work.
Thanks.